Marco Gori is one of the main persons who coined the term graph neural networks back in 2005, coincidentally at the International Joint Conference on Neural Networks. But he is also very well known for having contributed to this bigger field research area on neurosymbolic learning. That's there a picture of a Dachstuhl seminar around 10 years ago. But also very recently, he received the Test of Time Award on this area. So it's really great to speak about this different thinking of AI and not only brute force deep learning. And an incidentally also very nice to know that he can see the future, and there's proof of that. Back in 2007, he co-authored a book called Web Dragons. And this book raised already some early flags and some warnings what's happening when this development of tech and science continues, and there is this kind of monopoly in search engines and who controls who sees what information and finds what where. And that becomes recently more and more important in the area of generative AI. And what I just learned now as well, Marco, and then I will hand over to you, we both have a person of inspiration in common. My PhD advisor, Horst Bunke, is also a great friend of you, Marco, and you both like this alternative approaches towards neural networks with graph approaches as well. And that's why I'm very excited to hear from you what you have to say about lifelong learning intelligent agents. Please, Marco, the floor is yours.
Yeah, thank you very much. Thank you so much. And of course, I have to tell you, I'm frankly honored to. Can you hear? Is everything's fine?
We can hear you very well, and you will share your slides also.
Yeah, thanks. So, frankly, to say that I'm honored to be here, and especially in the framework of the International Neural Network Society, which is in fact one of the two societies together with the IEEE that since the dawn of neural computation during, at the end of the 80s of the past century, these two societies began popularizing in research the field of neural computation. And of course, we were mentioning the International Joint Conference on Neural Network, which is one of the most important initiatives that they organize in conjunction. And of course, is the primary scientific society in the field. And so I'm really pleased to tell you a few things about, what I'm believing, what I'm thinking about the current state of artificial intelligence. I think Marcus did a great picture, great introduction about, what I'm going to talk. And you will see two different parts. It's organized in two parts, 1 and 2. The first part
is start sharing your slides now, and then we can share your screen. Yeah.
I have to share. Yeah. Okay. Thanks. So I was telling you the talk is essentially divided in two different parts. In the first part, in the first part, I will give you a sort of big picture, of what is going to happen in neural computation and artificial intelligence nowadays. And in the second part, I will present briefly some intuition that I have. But I think that the most important part is definitely the first one, because I think it's covering something which is very connected to, what Marcus was mentioning. So let me tell you, first of all, what is my interpretation of artificial intelligence in a few slides. Essentially, I think if you look at the progress of the field, it's quite easy to recognize, remember what I like to call the connectionist wave, right? The explosion of neural computation during the 80s. And it's important to notice that the current explosion of interest in artificial intelligence is mostly due to the recent applications with, deep learning and large language models, this field that nowadays somebody called generative AI. And interestingly enough, there is a great role of companies, right? So the explosion of data from one side and the explosion of computation is what makes possible these wonderful, these spectacular results. But my interpretation is that, we have seen a number of important stages, but my interpretation is that there is a good chance that the actual breakthrough in neural computation was not essentially connected with deep learning, but probably years before with a connectionist way. So I'm thinking of the revolution that we saw, for example, in the parallel distributed processing research group and with other people who, contributed strongly on the field at that time. So I think it's the way which is currently supporting artificial intelligence. And from an epistemological point of view, my humble interpretation is that this is where we actually we actually had a strong transition in artificial intelligence. So let me just make touch a few things about the connectionist way. We have seen a huge number of models. I just want to mention one of the many popular and important learning algorithms that in my presentation are important simply because I want to stress the importance of neural propagation. So the deep meaning of neural propagation. And of course, many people in different ways contributed, right? So we can think of many scientists who gave the contribution in the field. Well, let me see what happened. I'm sorry, because can you still see? Yes, okay. So this is, of course, the backprop is one of the many, and there is an interesting story about backprop, right? But probably not many people realize is that, one of the secrets of backprop is the elegant scheme which is behind, for example, the importance, the efficiency in the computation of the gradient, right? So if you look at the computation, there is a secret behind, which is the traditional, factorization of the delta error and the output of the neuron. And this is extremely important, right? Because once you have this graphical structure, then you can compute efficiently the algorithm. And efficiently means that it is going to take a number of floating point operation, which is just proportional to the number of weights, not to the square of the weights, as it is normally assumed if you use any numerical algorithm. And let's say this is one of the secrets of the success. And so, for example, nowadays that we work with a lot of parameters, it is one of the secrets that you can appreciate, because if you don't have such an important and intriguing mechanism for neural propagation, you cannot actually compute the gradient and rely on important algorithms. But now I want to mention, I think, a seminal paper which was published by Francis Crick in 1989. And, Francis Crick, as you likely know, was part of the parallel distributed research project. And, concerning the excitement in neural networks, it made some intriguing notice about the biological plausibility. So I invite all of you to read this whole paper. I think it's a very nice paper. Essentially, it is noticing that there is no biological plausibility, and you likely know we have seen a lot of discussions on the plausibility of propagation algorithms like Backprop, and for many different reasons, Backprop is not considered plausible from a biological point of view. But interestingly enough, it's not plausible from a physical point of view because there is no time. So you may start considering recurrent neural networks if you want to consider at least the physical plausibility, right? But the role of time is crucial if you want to consider concretely the plausibility. And let me now show you a picture which shows, for example, how critical this issue is, right? This is an example of, a deep network in which, you apply in the traditional way the backprop update. And as you know, you need to keep the input fixed in order to have the backpropagation, right? But suppose you are processing a video or any sequence, of course, this is not good. It'd be very nice to have a sort of propagation, a sort of wave which, propagates forward. It may be a backward wave, right? And it could be great if it could be to have a sort of synchronization between these two waves for the computation of the gradient. If you look at these units, whenever you see the presence of the red and the blue, essentially you have available the input and the delta error. And it's possible in principle, to use a sort of backprop rule, right? But we are still back to the, traditional principles that already were, discovered at the beginning from the popular Hebb rule and many, subsequent analysis. So it would be plausible in case you start to think of the important role of time, right? But interestingly enough, I want to go back to what Marcus was saying during the introduction, right? Even if these computational schemes, if you look, for example, at nowadays architecture of large language models, and you think of, these transformers which work together, with the neural propagation scheme, the current neural propagation schemes, they are not actually incorporating time in the, let's say, in a deep sense, right? They process sequences, but the mechanism for the update of the parameter is a mechanism which is still based on, static processing. And the mechanism for the propagation, it doesn't really take into account time. But regardless of, this comment, regardless of biological possibility, now what is sure is that we have fantastic solutions, right, for dealing with real world problems. And in this picture, there is, the evolution of the dragon that Marcus was mentioning, right, in my book published years ago. And this dragon, is the dragon for generative AI. We have this, top-level research center in companies. And my understanding is that, they have been carrying out top-level research activities in this field. And my other impression is that it is also very difficult to compete from the academic side once, we have these technologies and this idea, which I think are quite mature. So you know, now, of course, that there is this idea that you can essentially interact with, let's say, Gemini, Llama, GPT, and you can develop top-level solutions from this interaction, right? But this milk is essentially produced by those companies. So I very much would like to restore the spirit that we saw decades ago concerning neural computation, and the rest of my talk will be devoted to changing completely, you know, the way of thinking. And so this is a presentation, you know, on what I call collectionless AI. So a different way of thinking of artificial intelligence where you do not rely on collection of data. And in this picture, you can immediately understand what I mean. This is the popular cartoon that is used by Norvig and Russell in their popular textbook, right? Where you see an intelligent agent which is interacting with the environment. There is perception, action, right? And of course, if you look at the book, many subjects of the book do not really require the access to data. It is the machine learning approach, nowadays machine learning approach, which is consuming a lot of data. But what if you think of designing machines which acquire intelligence by environmental interaction without recording the process information, right? So you are assuming to design machines which becomes intelligent, not because they have the pleasure of accessing huge collection of data, but simply because they live in their own environment. Of course, I'll go back to this issue because it's of primary importance in this talk. So this is a picture of the topics, the measured topics of the seminal Norvig-Russell textbook in artificial intelligence. As you can see in the green part, I clustered the topic of, you know, symbolic AI, and in the pink cluster, you see the traditional machine learning topics, right? And of course, there is a big difference, right? Because the green cluster is collectionless. You don't really need collection of data. You may need collection of rules, knowledge bases, but it's a different story, right? Completely different story. Whereas in machine learning nowadays, top-level technologies like those developing companies access huge collection of data. So what if you think of a completely different domain, right? A completely different subject, research subject, where you assume that even machine learning is based on the interaction, but not a collection of data. So you don't really enjoy the possibility of accessing data, but simply to interact with the environment. So there is a sort of challenge, right? A completely, picture of artificial intelligence. And I like, to show you this picture in which you see the evolution of computer science, right? So you started from IBM, so centralized computation. Then you remember personal computers. Nowadays, the intelligence is on the cloud. What if we go back to intelligence in small machines, right? So what is the possibility of moving, the intelligence to small machines instead of the cloud? So look at this, difference. From one side, nowadays you have intelligence on the cloud, foundation models. And from the other side, you can think of onboard intelligence. That there is a huge number of, computational devices on this planet, really huge, not only smartphone, right? Also, in industrial environment. And what is nice is that those devices are typically in a sort of, let's say, lazy state, right? They are a little bit depressed. I'm thinking of, let's say, a powerful smartphone, right? Which is simply, serving, maybe it is simply reporting notifications and not important stuff, right? So what if you start thinking of intelligence in the single devices, right? So nowadays, we mostly rely on collection, but we can start thinking of machines working just like humans, right? And this is why I told you we are somehow trying to restore the original motivation, the original principle of neural computation, where what I'm saying is not new at all, right? Because we were talking about artificial agents, their birth, life, reproduction, death, right? You can kill an agent, and maybe you can, from genetic fixtures, give rise to another agent, right? So it's a completely different way of thinking. But of course, the intelligence is on board in this case. And this is the main question, I think, right? Which is connected to my talk. And the question is, learning takes place without accumulation of data in nature, right? Is it possible to devise collectionless machine to gain intelligence skills, just like in nature? So that's the challenge. Because, during this talk, all of you are, listening my presentation, but of course, there is no recording in your mind, in your brain, right? So your brain is not recording just like a Zoom, which is in fact recording the details of the presentation, right? You are doing something different, right? You are processing the information that you are receiving, maybe while doing something different. And what is great is that you can simply use your intelligent capabilities for, let's say, just organizing your brain the useful information from this talk, right? So maybe use just a few bits, right? You don't really need to accumulate data. You simply need to provide an appropriate representation of what's going on. And that's the big challenge, right? It is exactly what happened in all animals, not just in humans, right? And of course, seems to be an issue which has nothing to do with biology. It looks like a sort of computational issue, right? So very important. So it looks like we have somehow to understand the laws of nature, which are, somehow governing the process of learning. And maybe later on we can go to algorithm, but probably it's important to understand a little bit what happens in nature. And so this is why, I think the pioneering role of people, like Hinton, I remember, those people like McClelland, for example. I had the pleasure of meeting recently McClelland, James McClelland, but now I saw in this, in this room, Professor Grossberg. There are a number of people who, at the very beginning, I think, for what I understand, were also thinking of something which is not just statistical machine learning. And so in this new perspective, my understanding is that we need to understand laws of nature concerning learning before moving to algorithm. And this is why in the rest of my talk, you will see a few ideas where I did my best to, give a sort of big picture of, one possible direction, right? Where the rule of time is definitely important, right? The so-called time, the classical time, the time that you see in physics, right? Because then, of course, in computer science, you have different interpretation of time, right? But we have to be careful when we use this notion of time. So there is another crucial issue that I think it's important as soon as you start to think of learning in this new framework, right? And the major remark, I think, is that it's typically very difficult to digest, the structural organization from big data collections, at least for humans, right? No one is exposed to university courses when he's a child. There is a process, right? There is an underlying process. You have to undergo steps of education, right? And these steps are important, right? So you see the crucial role of time that, for what I understand, as yet has been completely, neglected, right? So this is what probably we need to introduce somehow, right? And so in a sense, time becomes the protagonist of learning, and it is important to be able to focus attention and to have interaction with teachers, so to live in your environment. And this seems to be a computational issue more than a biological issue. At least that's my understanding. Now, let's see, what is in the remaining part of my presentation, a possible direction. As you see in this slide, I assume that time is the new protagonist, right? And so I'll do my best to, tell you of what I mean when I talk about laws of nature, because then we can move to algorithms. But it's important before moving to algorithm to understand, what is this framework. So if you look at this equation, right, I think you can start understanding what is my idea. Essentially, any textbook of machine learning typically introduced a so-called functional risk, right? So you are given your loss function, and then you have some probability measure, and you calculate the functional risk. And as you know, then you have these strategies which leads to the empirical risk once you have a big data collection. But one possibility, an alternative, could be that of calculating this average over time. Okay, so suppose you just replace this integral with an integral over time. Okay, well, if you look at from a formal point of view, you see the difference is that you simply have an integral over time. Instead of the loss function, you have still this loss function, but I prefer to call this function, by using the terminology of physics, I call this function Lagrangian, right? Because in physics, when you have an integral like this one, this is called a Lagrangian of the system. But it's essentially a sort of loss function, right? And you accumulate the loss over the life of the agent. Okay. As I was telling you, there is already a lot of material in theoretical physics, and there is a lot of tools, important tools, mathematical tools. So, for example, you likely know what happens of laws in physics, and for example in mechanics, right? In mechanics, if you take the action, you see here you have the kinetic energy and the potential energy, right? So you may have to candidate trajectories. You see this trajectory here and this imaging motion, right? And the question could be which one is minimizing the action, right? So these are a picture that I took from the classical Feynman lecture, right? Really very inspiring, you look at this minimization problem, and essentially, what is great is that it is exactly, this trajectory here, the actual motion, which minimizes the action. To be more precise, it is not really minimizing. It is essentially a stationary point, right? So there is a difference which is quite interesting when we apply this idea to machine learning. But so there is a very well-established theory of variational calculus, which make it possible to derive the so-called Euler-Lagrange equations. And essentially, the Euler-Lagrange equation return the motion of the particle. So given the potential, essentially you conclude that if you determine a stationary point of your action, the stationary point corresponds to the Euler-Lagrange equation, right? And essentially, these are the Newtonian laws at the end of the day. Oh, now, suppose you try to establish now some link with machine learning, right? What if you think of neural network where instead of talking about the position of a particle, you think of the weight, right? And then you have the velocity of the particle, but you may have the velocity of the connections, right? And then all the other mathematical apparatus, all the rest, for example, the action, the Lagrangian, the Hamiltonian, they are, very well developed mathematical concept that we can use. So we can reuse the apparatus of theoretical physics for, formalizing the learning process over time, okay? So I look at this picture. From one side, you have the law of mechanics, right? So you are given the Lagrangian, and you have the kinetic energy and the potential energy. And from the other side, you have the so-called laws of learning, right? And laws of learning here involve typically a loss term, which is, somehow similar to the potential of a particle. And then you have also, here is called a regularization term. This is the velocity of the change of the weights. So there is some intriguing analogy, right? There is this mass, which is, telling you how quick this update of the weights will take place, right? And in principle, you can also have a sort of gating parameter here, which is somehow telling you when the time has come for exposing your agent to a certain lecture, right? Remember my picture when I presented the student at school, right, with the teacher. Essentially, you need to expose your machine in front of a learning environment at the appropriate time. And this phi function here can somehow filter the information. So interestingly enough, if you are given a neural network, generally will be a recurrent neural network. This recurrent neural network is essentially a dynamical system. Of course, we can reproduce all these technical details in the discrete setting of computation. So I could use time discrete equation instead of continuous math. But, I prefer at this stage to use continuous math simply because it's more compact and elegant. But later on, of course, you need to involve the discretization. And if you think of this kind of problems, they are not covered only in theoretical physics. For example, if anybody in this room is somehow expert in optimal control, in optimal control, we do something similar, right? We want to optimize. In this case, we really want to optimize a sort of action, a sort of functional. We are not just happy with stationary point, right? And of course, there are some environmental interaction. You see in this equation, you see the state of your machine, then you see the weights, and then you see the environmental interaction, right? So U is just denoting the environmental interactions, right? So you are accumulating over time and look at the dependency, the temporal dependency also of the weights, right? So you have this dynamical system. And the idea is, what is a strategy? What is, the learning process over time? So you need to minimize this function. As I told you, the mathematics is pretty clear. So essentially, it is based, for example, on for people coming from computer science, it's dynamic programming, right? Nothing more than dynamic programming in the continuous set of computation. And we introduce typically the Hamiltonian function, and we have for optimization the Hamiltonian Jacobi-Bellman equations. Now, what is very important is that in order to think of a concrete solution, we cannot use these equations, right? Because they are typically the classical solution of optimal control, but unfortunately, these are partial PDE, partial differential equations. You need to know the boundary conditions, and we cannot use this mathematical framework for attacking learning problems. But interestingly, you could use their temporal translation, right? From a technical point of view, these are the Hamiltonian equations and are the characteristic equations of the previous PDE equations, right? Now, if you solve this equation, right, you see there is the state and the so-called co-state. Then, if you solve this equation, you essentially minimize the function, but you have to be careful. You have the possibility of minimizing the function only in case in which all your collection is available. So you are just back to the same principle of collection. In one case, you have the traditional statistical machine learning framework with the optimization of the functional risk. Here, we are landing in something very similar because we have a functional risk also in this case. I like to call this functional risk action because the terminology is similar to theoretical physics. I call this cognitive action, but there is a problem here, right? Because you need to know the boundary condition. You need to know all the interaction of the agent in order to learn, right? Whereas my principle of collectionless machines is that you don't want to store information. You just want to process the information as time goes by, right? So in principle, suppose you start from the initial condition of this differential equation, right? This is going to be a sort of recurrent neural network. Interestingly enough, it would be great if you could solve this equation, without using the boundary conditions, but simply by initializing, the state and then, having the interaction with the environment, right? But then you land in a different territory, which is, I think, really exciting, because now we are not protected anymore from math. You have to reinvent, something new, right? And the best way for presenting what I call Cognidynamics comes from, this difficulty, right? Which is very well, let's say, represented in this quote from this famous Danish philosopher. Life can be understood backward, right? But it must be lived forward, right? So I cannot enjoy the accumulation of all my life before learning. I have to learn as time goes by without recording information, right? And so that's the challenge now, right? So we start from this theory of this principle of theoretical physics, optimal control, but now, the challenge is how can we use this theory concretely, right? And so look at, with some more technical point of what could be a recurrent neural network. This is a recurrent neural network. You see, it's a recurrent neural network in the dynamic, in a dynamic version, but of course you can easily restore traditional models of recurrent neural networks. Or look at, that there is then a sort of cost index, which in my terminology is an action. You have a loss, which is essentially a potential, and then you have a regularization term, which is a sort of kinetic energy. And the other important thing is that you have some parameters, for example, some gating parameters. Look at parameters alpha and psi. Okay, you see they are essentially gating parameters, just like, for example, in LSTM, right? So there is this idea that you have to properly, control learning by these gating parameters. And I think, you know, the work by Smilhuber and others was important, right, for understanding how crucial is, you know, this mechanism. But there are so many contributions concerning gating. Now, you know, if you start using the math, the apparatus, the classical apparatus of optimal control, you know, it's pretty easy, right? You calculate the Hamiltonian function, and once you have the Hamiltonian function, essentially you can write your system dynamics, and you can write the learning, right? But what is important is that from one side, you have the classical Hamiltonian framework, and from the other side, this is the new issue. You have to learn these developmental parameters, so the gating parameters. And these gating parameters have to be learned in such a way that the optimality, instead of being based on boundary conditions, have to take into account the so-called Cauchy condition. So you start from the initial point and you interact with the environment. So this is, you know, where the new phase of learning comes, right? So optimal control from one side and energy-driven heuristics, which, you know, has to move the developmental parameters. So these gating parameters here, you see, this is a typical gating parameter, can be learned when we try to understand, you know, how the information can be properly filtered. Now, we will see in the next few slides that, you know, here we control the state and the co-state, and we will see precisely, you know, what they are in neural computation. Probably the best way for understanding what they are is, let's go back to the picture I presented at the very beginning, right? Remember, there was a typical neuron. I was thinking of a sort of forward and backward wave. So what happened if you look at the Hamiltonian equation? What is nice is that, you know, if you are patient enough to write down, you know, the Hamiltonian equation, you obtain these updating equations. Now, look at, you know, these are the equation of the dynamical system, the recurrent neural networks, and these equations here are the equation for the co-state. So, for example, in theoretical physics, the co-state is the momentum. So the typical, you have the conjugate variables. So you have the position and the velocity, right? So you have, this is the conjugate variable. In machine learning, what is nice is that if you look, for example, at PIJ, since I'm confident, you know, in the room, there are a lot of people who are very familiar with neural computational scheme. I invite all of you to check, you know, of the result coming from the computation of the Hamiltonian equation, right? You see, PI is really connected to the classical delta error of the backpropagation, you know, of all the backpropagation through time and, you know, real-time recurrent learning algorithm that you see. And you see the reason, right? Essentially, the computation of PI, the co-state, depends on the children. Whereas look at the dependency here, right? So you have a dependency on the parents when you calculate the state, and you have a dependence on the children when you calculate the co-state. There is an accumulation, the same linear accumulation. And if you look at this Pij dot, essentially, you know, this is a question which reminds the typical update of weights. You see, there is the factorization with the delta error and you know, the response of the neuron. So you somehow restore also the classical factorization of backprop, right? But there is a huge difference here, right? this is done locally, right? So for any neuron, you have this update, right? So you don't need to have the forward and backward step, keeping the input fixed, right? Here you have concrete ways which are, characterized by, this differential equation, which come from, the classical, dynamic programming. So that's the big difference, right? So I just want to quickly tell you that we can see that you can see there is, for example, something similar to gradient computation, right? You see Pij dot is essentially a gradient. Look at the factorization. You also see the prime derivative of the sigmoidal unit, right? So there is a very similar update mechanism. But going back to Francis Crick criticism about biological plausibility, at least what you see here is that you have a fully local computation. Fully means that the state of the unit of the neurons is updated locally by considering the parents in the graph, and the delta error is just updated considering the children, right? So you have waves. There is, an interpretation that can also be understood in terms of Lagrangian multipliers. And so I like this picture because it tells you that the interaction with the environment is based on some, reactions, right? And this reaction propagate, and this delta, so these Lagrangian multipliers are essentially the co-state that at the end of the day are, the delta error. So my final comment is that, there is a possibility, the new theory I'm proposing is a theory which is based on energy. Essentially, if you take the Hamiltonian equations and you use the traditional mechanism for producing energy balances, you end up in a principle which I think it's very inspiring for learning algorithm. Please consider that I call this principle because it's an energy principle, but it is in fact a theorem because, this equation can be derived from the Hamiltonian equations. And let me tell you what is the major statement here. Essentially, if you look at this, this box, this is the intelligent agent. You have an environmental energy. So there is an interaction with the environment by means of this, environmental energy. And then there is an internal energy. And of course, please remind the internal energy contains also a sort of loss function, a potential. And you want the potential to become as small as possible, right? And the other important thing is that you have a consumed energy, right? So you learn when you move those gating parameters. And so this is why the role of the gating parameters becomes really crucial, right? So we have mechanism for moving, those parameters with the purpose of consuming energy. So learning means to consume energy. And there is this beautiful, balance between what happens in terms of interaction, environmental interaction, and energy exchange with the environment, consume energy, and the effectiveness of this process. So my last slide is on this really new framework, because if you really believe that you have to change completely the way of learning, and you rethink of machines in a new framework where you don't have collections, you have small machines living in the environment. Well, in this case, there is not only the problem of solving tasks effectively. You also have to decide when the time has come to act, right? So maybe you can solve very well a problem. Maybe it's the time in a meeting in which you want to say something that it's good, but there is a good chance that sometimes it's better that you don't talk, right? So you have to actually understand when the time comes for taking an action, right? And which means that there is another level, which is a sort of, you know, you need to work at a higher level. You need a sort of conscious model. Of course, I'm just touching one of the many topics of consciousness. You know, this is likely one of the simplest mechanism, but yet you need to have a sort of conscious mechanism for deciding when the time has come for skipping, for example, you know, the interaction, and maybe to do something different or to act, right? So final comments. There is one part in my talk where there is a sort of proposal for all of you to think of, you know, a new way of designing intelligent machines, which is not based on collections. So machines which learn in, you know, in the ordinary, in the classical ordinary environment in which we live. Of course, it could be the case that we properly generate an appropriate virtual environment for the experiments, right? Instead of beginning immediately you know, working in the ordinary physical environment. You may have a simulation, right? Maybe you can help yourself also with foundation models and large language models for creating, you know, this environment. But then, of course, the challenge is how can we devise small machines which communicate and which, you know, solve tasks in this completely new framework, right? Without storing data, right? Just interacting. And then, you know, my 2 cents is, you know, this intuition that time plays a crucial role, and, you know, all the theory that we have in theoretical physics concerning primarily this Hamiltonian mechanism, these Hamiltonian equations can help approaching this problem with a major point that gating parameters, the tuning of gating parameters seems to be the most critical challenge. So thank you very much for your attention.
Thank you so much, Marco. That was really inspiring and interesting. And we have now the possibility, yeah, as you see, you have the possibility to ask questions. So when you have a question, maybe you raise your hand. You can share your video. You can share your sound. I see already a question there. So please, Tosin, go ahead.
Thank you so much for the wonderful talk. I was wondering if collectionless AI will be able to achieve the kind of performance that we have with current deep learning AI, especially for the fact that I have heard that humans are like few short learners. We also learn from, a few examples, maybe not as much as big data learning from several examples, but we still require a few examples to learn. So will collectionless AI really be able to achieve the kind of performance that we have currently?
Okay, so Tosin, thanks a lot for the question. Let me, the question give me the opportunity also clarifying, you know, what is the current state of this research, right? This is, you know, an invitation, right, for other people to consider, you know, this framework. What is important to say at this time is that we are really, really far away from, you know, a sort of competition, right? And probably competition with respect to deep learning, generative AI. But let me tell you more about the term competition, right? Because probably it is important to realize that if you really want to understand and maybe develop something new, you have to deeply understand what could be the meaning of competition, for example, with the spectacular capabilities that we have nowadays, for example, in large language models. My understanding is that it is not exactly especially at the very beginning the appropriate framework, and especially because even on the long term, even if there will be some really great theory with wonderful experiments, the kind of framework I'm thinking about is really far away, from the classical large language models and foundation models that we have, for a very simple reason, right? And the reason is primarily that, those models are currently, relying on a huge computational capability and huge collection of data. So they essentially know everything, right? So one beautiful thing is that they can speak in any language, right? They know nearly any topic of science, right? But interestingly enough, once you are in a very specific context, just like humans, just like animals, right? In most cases, you don't really need to know everything, right? So in most cases, people is not interested in knowledge of, let's say, philosophy, or let's say, biology, or it depends on your specific task, right? On very specific task, you can think of machines, which just like animals and humans can solve a task, right? In a completely different context, right? With respect to, those centralized, powerful machines. They don't have an answer for everything. At least they can communicate. So that's the perspective, right? At least they can communicate just like humans for, reaching knowledge, right? But they have a capability which is developed primarily because of the environmental conditions in which they live, right? So that's the difference in what I call connectionless AI, because they actually don't use data, right? They simply process information. That is a huge difference, right? Think in terms of privacy, think in terms of any issue connected to the accumulation of data, right? You don't really need to accumulate data. You simply interact. That's all, right? And you create in your representation in your brain an abstract description, right? In those neurons. So that's
Thank you.
Thanks.
Very nice. I had a bit of a similar question. I see it's a very nice framework, but did you perform any kind of experiments or something where you can show already the indication that this framework actually has promising advantages? I mean, theoretically, yes, but is there something which you have shown on?
No, that's also important, for me to make it precise, right, at this time. Well, at this time, we have carried out a lot of experiments, and we have, some evidence that there is the possibility, of learning in small, let's say, toy problems. So essentially the kind of environmental interaction that we consider is mostly at the moment that of, signals which, come from outside, and you have some supervision, right? And you want to see how, the supervision is properly, there is a proper tracking on this supervision. And then, for example, we are interested in generation processes, right? But let me tell you that it is really at an early stage. So experiments are, we have been working since, about 1 year on these experiments. And of course, I'll be pleased, for example, to share also a few papers that we have published for people interested, in knowing more about what happened, but also, for sharing code, because, we have a code which, implements the Hamiltonian, this Hamiltonian framework of learning, which at the end of the day, is very similar to the recurrent neural network learning, right? So if you think of the classical real-time recurrent learning, backpropagation through time, you think of the sophisticated algorithm behind LSTM, they are not really different, because the element which is strongly connected is the co-state, which is the delta error. So essentially, this is the link between this kind of theory and the traditional methods that are based on the gradient, right? So here, the gradient can, in a slide I was showing that there is the possibility, of approximating the gradient, but the movement is not exactly that of, the gradient, right? And what becomes extremely important is the role of the gating parameters. This is probably, the major challenge. And the intuition is that the gating parameters are expected to, let's say, focus on the most important problem when you learn over time, which is in fact that of, let's say, somehow construct a sort of curriculum of learning, right? So filter the information at the very beginning, and later on to start, pick up the information which is appropriate at a certain stage of learning. Because in principle, we are thinking of machines which, solve more tasks, not one, right? One of the beautiful issue here is that, these are living machines, right? So essentially, you assume that they process information continuously, right? So also in terms of experiments at the moment, we are carrying out experiments where, of course, just like everybody, is working on limited domain, right? But, in principle, you can say, okay, so go ahead and see what happens, right? Because you have interactions, and you are governing, the reaction to the different kind of interaction from the environment. But frankly speaking, going back straight to your question, I want to make it clear that we are really, really at the the research is still in its infancy, especially for the experiment. And my understanding is that there is a good chance, that what is important in this talk is not what, we have been doing, but maybe more, in opening the challenge of doing something really, really different, right? Because, the first part of my talk, I think, is, a challenge for everybody, right? The challenge is, what if you start thinking of computer science where we just land again on small devices instead of everything on the cloud?
Mm-hmm.
My intuition is that sooner or later, somebody, will find some very good solution also in this case. And going back to the previous question, right? I think in no way this is going to cancel, even in the more optimistic prediction, is going to cancel the great technology that we see nowadays, but it could be, in principle, a challenging mechanism, right? Think of a personal assistant, right? A personal assistant which is always with you and which doesn't distribute the information with others, right? A personal assistant which don't store the information on the cloud, but it's simply, with you, I think on the long run could become something particularly important. But think of application in industrial domains where, you actually want to have machines living, in a certain chemical environment, right, for making predictions.
Thank you. If there are people who have more questions, please. I think we are only around 20 people in the room, so just speak, or if you want to write in the chat, you can also write. Give it a short minute. On the other hand, currently we are still recording. Maybe some people don't feel too comfortable about it. Marco has agreed to stay available online for other questions later on, once we close the seminar.
Yep.
Anyone else having a question? Please go ahead, Danilo.
I have a question. Marco, thank you very much for your wonderful, wonderful talk. I know you are also interested in more conceptual and philosophical aspects of neural networks. May I ask you, the development of neural networks has been, shall we say, pre-scientific. So there's nothing wrong with pre-scientific heuristic. The Egyptians have built pyramids without understanding all the civil engineering about that. They had the know-how. So in neural networks, we have plenty of know-how. Don't do this, do that, do it this way, do it that way. If it doesn't work, add one more layer and such like. Where do we see it going as we move towards huge networks? Can we really afford to develop our network in a pre-scientific way? Or, as you very nicely showed on various Hamiltonians, Lagrangians, and such like, is it feasible, plausible to use scientific methods at such a large scale?
Yeah, well, if you look at the results, right, the current results from companies, of course, everybody is understanding that we have fantastic, spectacular results, and I know a lot of people also, involved concretely in these experiments. And my understanding is that nobody was actually believing that those large machines could concretely come up with these extraordinary results. So, which is very much in line to what you said at the very beginning, right? That sometimes things happens and you don't really know why this happened, right? And so I'm confident there will be still investigation, and still we probably still need to understand a lot of things about what is the effect of the scale, right? Because the effect of the scale has been really fantastic. You see the big difference. I was mentioning, the difficulty of competing, with this research center in large companies, simply because of the scaling, simply because of the availability of data. And so going straight to your question, I think that we probably have still to understand better, right? What is the reason why they are working so well? There are some interesting intuition that are circulating. We have seen also a few inspiring papers, but yeah, I think understanding is still at an early step. When you move to what I was proposing and you introduce time, well, I think you probably really open a completely different door, right? Because at the end, if you really look at one of the reasons of the success, for example, of large language models, one of the reasons is, of course, everybody is talking about transformers, right? And in GPT, T is transformers, right? So it makes sense. But my understanding is that, yeah, this is one of the reasons. But there is another one, which is probably, at least in my understanding, much more important. And is that, you process information continuously. You have a regression model, right, which can make prediction of what comes next. You have a huge collection of data. And this has been one of the secrets, right? So to have this processing, this temporal processing, right? And this is definitely a completely new picture of learning, because those gradient methods, if you think carefully of, what is the meaning of the gradient, you know how difficult it is when you talk with students to teach a stochastic gradient. For example, for stochastic gradient to work concretely, you need some assumptions, So what happens in those methods, right? The extreme evolution of what we have been observing now is the introduction of time. Because, in this case, you can process information continuously. You don't have a limitation of data. The big difference, in my proposal is, what if you don't really need to accumulate and you process? And in this case, probably you need to understand better the kind of theory which is behind the learning process, right? So at least that's my humble attempt, right? To see how we can, have a mechanism for training recurrent neural network this time. And since you are, expert in the field, and, you are very familiar with recurrent neural networks, you see one small contribution in what I presented today is, for example, that you finally have algorithms that are fully local in both time and space. So you have this possibility, of getting rid of, the length of the sequence. So the length of the sequence is not an issue anymore. The issue is that, you have an overall index during your life, and you have to see, how you work. And in this case, I think we really need the theory. On the other hand, for what we have nowadays, even without theory, as you have seen, the results are really fantastic. Maybe we need to understand, but are already very good.
Thank you. Thank you, Marco. And I think we are now at the end of the time slot. Thank you so much for the presentation again. And Danilo, maybe you noticed I'm wearing today the INNS pin, and I am sure Marco also has one. Just want now also to, first of all, thanks again, Marco. And I guess many others are also very thankful. We cannot applaud like in a real conference. Just want to give a bit of a view to the future. We have already a confirmed next INNS webinar session, and that one will be by Ryan Sampson on AI for finance, which is also a very hot and interesting topic. And I think the most interesting one is because this is from a practitioner's point of view. So he will give really some practical insights, how the useful large language models or other neural networks are and what really works. Also, we are discussing, but it's not 100% sure yet, mark already in your calendar in 2 weeks from now, the 21st of November at the same time slot, where we want to discuss about AI for education. And just recently, we have also identified who will be our INNS annual lecturer. That's like once a year, we make one bigger webinar, and this time it will be Vladislav Dush, who will speak about a very interesting topic. It's not really clear what his title will be, but it will be in line with the novelization of neural networks. So we know just this year 2 great researchers have achieved the new Nobel Prize in Physics, and these were neural network researchers. But he will also speak about current and future perspectives. We will announce the time slot, the date, and the exact title very soon, but I'm already excited to listen to Professor Dush. To get informed and stay updated, of course, you can follow us on LinkedIn, the INNS Society. But even better is if you become member of INNS, the International Neural Network Society. There is a barcode which you just can scan. And of course, we provide you with links in the text beneath the video after this recording is online. And what I would really love to do is to meet you now in a coffee break and have some nice foods and sweets and discuss a little bit more casually with you. As I mentioned earlier, Marco will still be around for some post-recording discussions, but this physical meeting has to wait until our next International Joint Conference on Neural Networks. And that is planned to be in Rome, Italy, in the end of June, beginning of July, and you still have more than a month to submit your papers, and I'm very sure that you have also great contributions for the International Neural Society. And please, here are again the barcodes, register to INNS or submit to the Joint Conference on Neural Networks. Thanks again for today. Thanks, Marco, again. Thanks also everyone who was in the audience, everyone who asked questions, and see you again in 2 and 4 weeks from now.
Thank you.